Hello everyone. Today we're going to introduce design for static loading again. Last time we have already introduced maximum shearing stress model. This model is the most conservative model that we're going to introduce in the class. Based on all the load conditions that we investigated, if we are working on a plane stress problem, on the plane, if we study the principal stress, one of them is SA, the other one is SB. And if we plot out the design limit for both principal stresses, this is what we get at the end. This hexagonal shape is the original limit based on maximum shear stress. If we apply safety factor into the model, then we have a smaller hexagonal shape. So our design region becomes smaller. We cannot handle greater loads, but our design will become safer. Okay? So those boundaries were determined based on the equations that we derived in the last time. I wish you could spend more time on reading them, understanding them based on the previous lecture. But today we're going to introduce another model which is less conservative. So we could be having a greater design space. When our design space is small, we are conservative. We don't allow a design to carry greater loads. If we have a design point outside of the region, it's carrying greater loads, having greater stress. We don't allow that. But if we have a less conservative, more aggressive design, it's possible that we could have a design outside of this hexagonal shape. We will show you how this model looks like. And the way we derived this was based on energy model. So let's focus on how this could be derived. This model is called maximum strain energy model. So everything was based on the strain energy inside the material. Consider this material is under elastic loading. It's having like a spring is having linear deformation. So just like a spring, when we compress a spring, there's energy stored inside the spring. It's called the strain energy. So if we release it, the energy will be released. Based on that concept, we could derive so-called the maximum strain energy model. Now, let's start from, how about we talk about the drawing first. So let's say under this particular coordinate, x, y, z, we observe a small piece of the material, the white box. And how do I know it's a small one? Because the width is dx, dy, and dz. Just a tiny piece of the material from your design. Since it's a tiny piece, we assume the deformation inside is linear. So we are still in the elastic deformation region. We are not talking about yielding. Okay, this is only under yielding. So this is elastic mechanics. That because of those reasons, you can see a lot of equations. They are linear equations. Okay, if we have large deformation, then many of the equations may not work. Okay, so let's take a look at this material. It's under loads on 3 different directions, x, y, and z. Okay, and after we stretch the material along 3 different directions, the material expand a little bit in each direction. So for x direction, the width right here is dx. It was lengthened a little bit, and we don't use d anymore, we use the delta. So delta x is much smaller than dx. It's a even smaller dimension than dx. It's the deformation caused by fx. Similarly, along y direction, we have delta y due to the force on y direction. And also on z, we have deformation of dz, delta z, sorry. Okay? Now you understand this drawing. Let's take a look at each portion of the derivation. First part, let's talk about stress. Since we have pure tensional force on each direction, so we can easily calculate the stress, the normal stress on each direction. So we will have normal stress x equals to the force over the area, the stress area. And for this equation, the area would be dy times dz. Okay? Similarly, sy equals to fy over dz times dx, and also sz equals to fz over dx times dy. This should be pretty easy. Basically, force over area equals to stress. Now, in the second portion, we are gonna recall the definition of strain. Strain basically is the amount of deformation over its original length. So for strain along the x direction, the deformation is delta x, original length is dx. That's why strain x, epsilon x equals to delta x over dx. Similarly, we can have the other 2 equations over there. Now, the third part we're going to talk about is based on elastic mechanics. Since we are analyzing everything inside the linear region, so the Hooke's law works. Okay, so what's Hooke's law? Hooke's law basically describes the linear relationship between the stress and strain. However, the complete format of Hooke's law introduces the Poisson's ratio. So when I pull, for example, up and down, when I pull, the amount of stress I generate is linearly proportional to the strain along this direction. However, when I do this, on the horizontal direction, it will shrink a little bit. Okay, it will shrink a little bit. So since we have forces on each direction, I know the force along this direction will make this direction become longer a little bit, will stretch a little bit. However, when I'm also pulling from the side, so the pulling force on the side, the stress on the side, will make this up and down direction shrink a little bit. So that's why we have a minus sign here. This minus sign describes how much shrinkage we will have based on the strain along the other direction. And the ratio is related to the Poisson's ratio. Okay, so if you don't remember what's Hooke's law, you should go back and check your solid mechanics textbook, and we are not going to spend too much time on this. Okay, so now you understand we have definition of stress, definition of strain, and also the Hooke's law is valid. Now, since this is a maximum strain energy model, we should try to derive the elastic strain energy based on the deformations that was caused by the three forces on each direction. And we know for spring, the strain energy equals to 1/2 times F and times delta x. 1/2 Fx, right? 1/2 of Fx. This is something we already know in the past, so I'm not going to derive this. If you forget, basically spring force equals to the spring force equals to the spring coefficient times delta x, right? So the work you generate based on the you perform, the work you do will be stored as strain energy. So the work done equals to F times delta times delta x. But because the force depends on your delta x, so maybe I should make a drawing here, so it will be easier for me to explain. Right, so this is how much delta x you have, and this is F, and this is K, right? So more force apply, more deformation that you will get, and they are having a linear relationship. And the work done basically is the integral of this part. So when you try to calculate the integral, it's actually 1/2 of F times delta x. Okay, this is what I want to try to say. I couldn't explain well when I don't have a equation and figure right there, but now I have it. It will be easier for me. Okay. So this is basically what we are having here. Okay. This is, we treat a material like a spring, and the strain energy basically is the integral right here. So 1/2 of the force multiplying the deformation. But on the other coordinate, we are also storing strain energy. So we also have the elastic strain energy stored along due to the force applied at the y direction and z direction. So we can start to put what we have derived into this complete equation. F equals to Sx times dy and dz. So we can replace Fx by what we have right here. Okay, and also delta x equals to strain epsilon x times dx. So epsilon x times dx. Okay, similarly, you can do the same thing. You will get what you have right here. Okay, and then we will apply Hooke's law, and then we will replace the epsilons. Okay, once we do that, all we have at the end are in the function of sy, sx, sy, and sz. Okay, as you can see right here, and of course there's a Poisson's ratio right here. Okay. Now, if we talk about elastic strain energy per unit volume, then we define this as a small case u. Then this equals to the capital U over dx dy dz. This is like the total volume of that tiny piece of material. If we do that, at the end we end up with an equation like this. Okay, we can go back and see what we had earlier right here. Okay, basically when we have u over dx dy and dz, at the end we have something like this. Okay, a long equation. You don't need to memorize it, but this is what we get. Okay, then what? We are going to go through the same procedure that we have talked about in the past. What procedure? We would like to go back to tensile test. Okay, so this is more like a general equation. This is the elastic strain energy that is stored inside this unit volume based on forces along x, y, and z direction. How about tensile test? When we are only pulling a material from along one direction, that's tensile test. When that's the case, we don't have forces along y and z direction. That's why all these terms become zero, and we end up with a very simple equation like this. And remember, there's an idea about the limit under the tensile test is when the material is under the stress that is exactly the same as yield strength. Okay, when we enlarge our pulling force and we generate greater and greater stress, and when this stress is reaching the yielding strength, that's the limit. You cannot pull anymore. So for that extreme situation, what would be the elastic strain energy? The elastic strain energy at that particular limit state equals to this. So it seems like for any material, this is the maximum elastic strain energy you can have. You cannot have a greater amount of strain energy, which means your material may be stretched too large if the strain energy is greater than this value. So this is the limit of elastic strain energy per unit volume. So apply this to our general equation, we realize the elastic strain energy per unit volume should be smaller than or equals to this limit that we just derived. Okay, if that's true, then we can get rid of some coefficients that is the same on both sides. At the end, we end up with a long equation where you can only see principal stresses along three different directions, and also Poisson ratio and yield strength. So this becomes our the final derivation of our model. This is the maximum strain energy model. Okay, and this is the general equation for a 3D loading case. How about we reduce it to a plane stress problem? When we do that, we don't worry about the z direction, so those disappear. And at the end, we have this much simpler equation. This is the maximum strain energy model for plane stress or plane strain problems. Basically 2D problems. Okay, and I try to plot out the boundary of this equation. At the end is this ellipse, the tilted ellipse that I'm drawing on the right hand side of the slide. And if you are interested about how I draw this, it's basically right here. I rotated the coordinate by 45 degrees. At the end, I have this SA prong and SB prong, and the SA prong and SB prong will have this relationship with SA and SB. Basically, this is a rotation matrix. So I can derive how SA and SB will be related to SA prong and SB prong. So once I have that, I can plug it back to the original equation. When I do that, I replace every SA and SB. I end up with a new equation where I only have SA prong and SB prong to complete this 45-degree rotation. So basically, we are studying along this 45-degree red-colored coordinate. And when I do that, if you continue to reduce the equation, you end up with something like this. And if you have an idea, this is an equation of an ellipse. So you can make a drawing of it, and at the end it looks like this. I will allow you to spend some time to make the drawing by yourself. So this is a shape that's gonna pass through some points that we know in the past, basically the same point that we passed through in the past. However, we have a greater space right here and also a little space right here. So as you can see, the maximum strain energy model is a little bit wider, bigger, larger than the maximum stress model, which means this model allows us to take greater stress. So if originally we have a design right here, it's safe for the maximum stress shear stress model. But if we have a design on the top, which means we are carrying greater stress, for maximum shear stress model, it's not good. It's outside of the boundary. But when we are using maximum strain energy model, it's okay. It's still within the ellipse. So from here, you can tell the maximum shear stress model is more conservative. And the maximum strain energy model is less conservative. You can take the risk. You can become more aggressive. Okay, so it really depends on whether you want to be conservative or not in order to pick up the right model for you. Okay, next, how about we introduce safety factor to maximum strain energy model? The way to do it is exactly the same. You put an safety factor on the bottom of the right hand side, and what's gonna happen is that you are going to have a ellipse, a smaller ellipse, and also passing through what we had earlier, passing through the same 4 points, and also slightly greater than the maximum shear stress model with safety factor. Okay, just for you to know, our design will shrink a little bit when you the design limit will shrink a little bit when you have safety factor. Okay, so this will be the final equation that we will use for the course. Now let's try to solve a problem. So consider this plane stress problem, and we the stresses are being shown in the figure. And if you plot out the Mohr circle, it looks like this. I will allow you to try it by yourself, and from here we can calculate the maximum shear stress, principal stress, both principal stress. So here the magnitude is 42.4, S1 equals to 54.4, S2 equals to negative 32.4. I will allow you to try it by yourself. And let's say this material is having a yielding strength of 100 megapascal and having a Poisson ratio of 0.3. What's gonna happen? Let's try it. If we use maximum shear stress, like I said earlier, you can directly use the equation. This is fine because all the hexagonal boundaries all were derived from here. So you can directly use this one. That's totally fine. Since we already have this, we can just place it here. This is our yield strength. By this equation, we have a safety level of 1.18. Same material, but we have a safety level of 1.18 only. Now let's think about let's try to use maximum strain energy model. So this is the one, and we plug in all the numbers that we know from here. And when we solve it at the end, the safety level become greater. So for the most conservative model, the maximum shear stress model, we only have a safety level of 1.18. However, when we choose the maximum strain energy model, we could have greater safety because we think we are actually safer when we are less conservative. Okay, this is how you how those numbers represent. When we have a design with greater safety factor, greater safety level, it means we believe our design is safer. But when we believe we have a lower value of safety level, that means we are very conservative. We want to be even safer. We believe we are not that safe. Okay, so in that case, maybe we will make our design stronger, using stronger materials, thicker, bigger, but heavier. Okay, so it really depends on which model you would like to use. Okay, so in our lecture, this is the most conservative one, maximum shear stress, and this is the most aggressive one, maximum strain energy model. Next time I will introduce you another model which is in between. It's not the most aggressive, it's not the most conservative, it's in between. That's why the next model is very popular. Everybody use that one. Okay, so I will see you in the next video. Bye bye.